Hello student, today we are going to study about entropy of a mixing and its deviation. At first, let us know what is entropy of a mixing. When gases are mixed with each other, then there is accompanied by change in entropy. This change in entropy is called entropy of a mixing. It is denoted by symbol del Yes, yum. This is del sm. It is symbolized by del sm. That is del sm is equal to del s1 plus del s2. Del s1 means entropy change by first gas, and del s2 is equal to entropy change by second gas. Now we'll derive the expression. The question may ask like this: derive an expression of the entropy change of mixing of ideal gas. We know entropy change of gas del S is equal to Cp ln T1 by T2 R ln P1 by P2. This we have already derived from the entropy for change of a gas. This comes from the entropy change of a gas which we have already derived in our previous lecture. In isothermal process, temperature remain constant, so this term whole term becomes zero constant, and so the remaining term is R ln P1 by P2. At isothermal process, del S is equal to R ln P1 by P2, and for n mole of gas, del S is equal to nR ln P1 by P2. This is at 1 mole of gas. If we take it n mole of gas, then n comes here, and for the first gas del S1 we take n1 R ln P1 naught by P1. Instead of P1 we use here P naught. For second gas del S2 is equal to n2 R ln P2 naught by P2. This is equation 2. And mixing total gas. Now mixing total gas means adding del S1 and del S2. If we add del Sm is mixing of a gas, adding del S1 plus del S2 is equal to del S1 is equal to n1 R ln P naught 1 by P1 plus n2 R ln P2 naught by P2. This is equation 3. According to Dalton's law of partial pressure, for first gas P1 is equal to N1 P1, and for the second gas P2 is equal to N2 P1. We take P1 and P1, but just this mole is changed here, where N1 and N2 are the mole fraction of two gases. This N1 for first gas and N2 for the second gas. Putting the value of P1 and P2, we put this value P1 and P2 in equation 3. We get the relation like this: del Sm is equal to N1R ln P1 naught by P1 was there, and instead of P1 we write N1 P1 plus N2R ln P2 naught by P2 was there. Instead of P2 we write n2 P1. Let us assume that P1 naught P2 naught is equal to P1. This P1 naught and P2 naught is equal to P1 we assume, so that del Sm is equal to n1R ln, instead of P1 naught we write P1 n1 P1 plus n2 R ln, instead of P2 we write P1 by n2 P1. Now del Sm is equal to n1R ln. This P1 and P1 is cut down. This P1 and this P1 is also cut, so that n1 remain here and n2 remain here. Del Sm is equal to minus this. Whenever we use ln 1 by n is equal to minus ln n. We use this formula here. This is the formula. We apply it here. Minus n1 r ln n1 minus n2 r ln n2, and we take minus common from here, and remaining term is n1 r ln n1 plus n2 r ln n2, which is the required expression for mixing of ideal gases. The change in entropy when there is mixing of gases, which is the required expression. This equation shows that total entropy of mixing of gases is independent of temperature. It is independent. Here is the temperature is not used. Temperature is the deviation is free from the temperature, so it is independent from the temperature. Here n1 and n2 are less than empty. Here n1 and n2 is less than empty. If n1 is kept, n1 and n2 is equal to 1, then it will be 0. If ln1 is equal to ln n2, then it 1. If we use 1, it will be 0. If n1 and n2 is taken, n1 and n2 is greater than 1, then its value will be positive. If we take less than n1 and n2 less than 1, if the value of n1 and n2 is less than 1, then it will gives the negative value, and with be out of results the relation is equal to positive. It gives positive value. Okay student, I hope you understand this, and please like, comment and subscribe my channel. Soon I'll provide you a new video. Thanks for watching my video.